Hi everybody, thank you for coming to watch this Canadian Academy Physics video. In this video we're going to be covering the second half of nuclear physics concepts, which are inclusive of week 14 material. And we're going to start with radiation penetration. And so in week 13 we already covered the introduction for alpha particles, beta particles, and gamma photons. But now we're going to talk about their radiation penetration depth. And so alpha particles, as we know, are positively charged, and that means they have two protons, making them essentially a helium-4 nucleus. But because these particles are so heavy relatively in comparison to beta particles and gamma photons, these particles are going to have difficulty penetrating very far. And so with that, they're going to be stopped by only a few centimeters in air. And so alpha particles actually have the lowest penetration depth. And so beta particles, as we know, can be either positively charged or negatively charged, depending on whether it's a positron or electron. And we know that positrons and electrons have virtually no mass, so they're going to interact. Less with their environment than the alpha particles, so they won't. So they'll be able to penetrate further into objects. And as you can see here, they will be stopped by roughly a meter in air or a millimeter in aluminum. And so gamma photons are the last particle that we're going to talk about. And these aren't really a particle because they don't have any size, mass, or charge. And so for that, they interact the least with their environment relatively in comparison. And so the gamma photon will have the ability to travel the furthest or penetrate the furthest into an object. And so we're going to cover briefly the factors affecting the range and penetration of radiation. So first, we already said that the penetration depth is dependent upon a particle's interaction with the environment. But additionally, the larger the energy the particle has, the increased range or the increased depth this particle will be able to travel. And this is evidenced by the fact that gamma rays actually have the largest energy on the electromagnetic radiation spectrum. And so as a result, a gamma photon will have the ability to travel the furthest. And so next we have material here. Whenever you have an increase in electron density in a material, it's going to result in a decrease in range for a particle or the photon, because the particle is going to be more likely, it's going to have a greater interaction with the environment. And then so lastly, the type of radiation, as we've already prefaced, that gamma photons have the highest penetration, whereas alpha particles have the lowest. And so what I want to talk to you about next is radiation damage, and move into radiation absorbed dose. And so previously we saw that we were able to calculate the decay rate of a radioactive substance as the number of nucleus decays or particles per second. But this doesn't really account for the amount of energy that is being emitted into a body. Because although we can count the number of particles that are decaying, particles have the tendency to have different amounts of energies depending on what atom or element you're considering. So there was no way in determining the amount of energy that's being lost. And so we needed a method of defining the energy that's deposited into a body. And so this is where we came up with the radiation absorbed dose, or the RAD. And so the radiation absorbed dose is basically the energy that's deposited into a matter per unit of mass. So that means that if you had 0.01 joules of energy per kilogram, then you would have 1 rad. And then, so this is very significant for radiology and radiological protection, because it's important to measure the amount of energy or the amount of radiation that your body's being exposed to, so you can sort of limit the damage. And damage is what we're actually going to talk about next. But so what you need to know about rads are that they are a measure of the amount of energy per unit of mass that you're considering, so per the amount of target tissue that you have. So if you were to consider your whole body, and you had, let's say you experienced 30 joules of energy, and you weighed 25 kilograms, then that would be you could be able to convert that to rads by using the conversion factors here. So like I said, we have 1 rad is equal to 0.01 joules per kilogram, and if you like this a little bit better, then you can say 100 rads is equal to 1 joule per kilogram. And I didn't write it here, but one joule per kilogram is actually equal to 1 gray. And so we can write gray here, and this is abbreviated as GY. So this is rads and gray. And so this is going to come up a little bit later. But the next thing that we're going to talk about is how this energy relates to damage. And so now that we know a method for determining the amount of energy that's deposited into a body, we still didn't know exactly how this related to the amount of damage to the body. So we needed a method of defining the effectiveness of the energy or the radiation in causing damage. And so this is where the relative biological effectiveness comes into play, or the RBE. And so we know that alpha and beta particles and gamma photons elicit different amounts of damage to a body or to an object because they have different amounts of energy. And so we needed something to allow us to compare the relative ionizing radiation to one another. And so this relative biological effectiveness is actually just a factor that compares the effectiveness of one ionizing radiation relative to another. And so the higher the RBE that we have for a type of radiation, the more damaging this radiation is going to be when it's deposited into a biological tissue. And so if you need help understanding what RBE is exactly, I'm going to take you down here. We have what says 1 rad of alpha particles elicits 10 to 20 times more damage than 1 rad of X-rays. So this means that if you had 1 rad of alpha particles, then it would elicit the same amount of damage as 10 to 20 rads of X-rays. So therefore, your RBE for alpha particles will be 10 to 20 because it's always relative to the amount of X-rays necessary to compensate for the damage caused by the alpha particles. And so here's the like sort of a summary statement. RBE is essentially the number of rads of X-rays producing the same damage as 1 rad of the radiation in question. So that, like I said earlier, alpha particles, their RBE is 10 to 20 because they require 10 to 20 rads of X-rays to equal the same amount of damage caused by 1 rad of alpha particles. And so as you can see in this table, or as you can see in this sort of flow diagram here, alpha particles have the highest RBE, meaning they are the most damaging type of radiation per unit of energy deposited in biological tissues. And then afterwards, beta particles, gamma photons, and X-rays all have the same amount of RBE. And so next we're going to talk about how these two sort of fit in together. And they come together when you consider the Roentgen equivalent in man, or REM, or REM. And so REM is just a unit of equivalent dose, or an equivalent dose is just defined as the dose quantity affecting health. And so REM basically aims to convert the physical quantity of radiation absorbed dose and take into consideration the relative biological effectiveness to quantify the health risk to the human body. And so this is basically saying that we can quantify the amount of energy going into a target tissue from the RAD, the radiation absorbed dose, and we know how the relative damage from that energy is dependent upon the relative biological effectiveness. So we're basically taking the RAD times the RBE to get the to get the REM, and the REM is a unit for quantifying how effective the energy, the radiation is in damaging the body. And so we can use another standard unit of measurement in sieverts, or SV, and this is 1 GY, which we know is equal to 100 rads times RBE. Or like I said, we can use 100 rads because that's equal to grays times RBE. And so from this we see that 1 sievert is equal to 100 REMs. And so this table here summarizes the units for radiation that you might use moving forward. And so next we're going to talk about something that's sort of unrelated, but we're going to cover the typical photon energies. And so here are the ranges of the amount of energies per photon of electromagnetic radiation, with visible light having the least amount of energy in comparison to these three. But as we know from the electromagnetic spectrum, that radio waves actually have the least amount of energy because they have the largest wavelength. But for these three types of electromagnetic radiations, they can actually be considered as ionizing radiation because they have the ability to remove electrons from atoms and break chemical bonds, specifically in water. And they use water to sort of gauge whether or not a type of radiation can break apart those bonds. So we know that basically anything larger than then 4 electron volts can have the capacity to break a chemical bond. But the thing is, the UV spectrum or UV light, not all of it is capable of ionizing a molecule. And so we broke down the UV spectrum into these 3 categories. UVA, which is the lowest energy range or the highest frequency of ultraviolet radiation. And so this UVA, ultraviolet light A, does not have sufficient energy to actually ionize the water molecule, which we use to prove that that radiation has the potential to ionize. And so when we look at UVB, UVB is actually the first UV light to be able to ionize a water molecule, and UVB sits around 33 electron volts for energy. And so you would be able to convert that to frequency to find where on the electromagnetic radiation spectrum it sits. And so UVC has the highest energy range of UV radiation. So this definitely can ionize a water molecule. So next what we're going to talk about is also unrelated to what we were talking about previously, but we're going to cover radiation and the biological effects to DNA. So basically there's 2 methods through which radiation can affect DNA. We have a direct action mechanism and an indirect action mechanism. So a direct action mechanism, as you can see from the diagram, is when radiation creates ions, and these physically break the DNA backbones or base pairs. And so this doesn't need any intermediary. The radiation can go ahead and simply break these bonds right here in the DNA double helix, whereas in indirect action mechanism, it requires the creation of a free radical, which is just an atom or molecule with an unpaired valence electron. So it's highly reactive because it wants to fill that empty spot in its valence shell. And so it creates the free radical from a water molecule. So you see how this radiation interacts with the water molecule to create the free radical by ionizing it. And this free radical will cause single or double stranded breaks in the DNA backbone. So here's the 2 sort of mechanisms through which radiation affects DNA. And so next we're going to talk about, we're going to go ahead and move into nuclear fission and fusion. Nuclear fission occurs when a heavy nucleus splits into 2 or more light nuclei with the emission of neutrons. And so this is going to make a lot more sense. This page has just words on it, but I have a diagram here that I can walk through with you also. But you should note that this process of nuclear fission can either be induced or spontaneous. So the splitting of the heavy nucleus can be induced by a neutron, or it can happen spontaneously without any external support from the environment. And so an induced nuclear fission, like I said, involves a neutron, and this results from the absorption of that neutron, and it sort of results in the nucleus being deformed. And then as we'll see a little bit later also, once this nucleus deforms, it's more likely to be overcome by the repulsive Coulomb forces, and which will overcome the nuclear forces attracting these nucleons together. So once this neutron comes into contact with the nucleus, the nucleus will deform to where the nuclear forces are no longer the strongest force affecting the nucleus. So it results in the break of a nucleus into 2 or more nuclei. And so once this nucleus will break, it's actually going to release energy as kinetic energy for the reaction products, which will be additional neutrons and these lighter nuclei fragments. And so once these if you have a certain amount of neutrons being broken, then they can result in, or not broken, but ejected from the nucleus. Then it can result in a chain reaction, and a chain reaction occurs when these additional neutrons that are ejected with the lighter nuclei will induce more nuclear fission at other atoms, because we know that the nuclear fission started from the absorption of a neutron. So when we're producing a neutron from the fission of a nucleus, then those neutrons also have the potential to induce more nuclear fission. And so it's also dependent on a few other factors, in that in order to sustain a chain reaction, it must then the nuclear fission must require on average a release of 1 neutron per fission. So that neutron can go ahead and induce more nuclear fission. And then so also we need an amount of nuclei greater than or equal to the critical mass. And the critical mass just means that it's the smallest amount of fissionable material that can sustain a reaction. So moving forward here, this might make a little bit more sense on this diagram. But what we see here is we have a nucleus, and then as we know, the nuclear force is holding the nucleons together to form this nucleus. But we also know that the individual nucleons are sort of repelled by one another from the electric force, but the electric force is not strong enough to overcome this nuclear force. But once we have an absorption of a neutron, or a neutron comes into contact with the nucleus, it has the ability to critically deform this nucleus to the point where the electric forces are now stronger than the nuclear force, so it will result in the splitting of this nucleus. And so this is seen here, the full nuclear fission timeline here. We have a neutron coming into a contact with a heavy nucleus, and then this will result in a critical deformation of the nucleus, which will ultimately split this one nucleus into two lighter nuclei and result in energy release, kinetic energy for these lighter nuclei and further neutrons, which can go ahead and have the capacity to start another chain reaction. And so just very briefly, like I said, nuclear fission can either be spontaneous or induced. And so spontaneous nuclear fission occurs primarily in heavier nuclei because these heavy nuclei have a decreased stability. And so this decrease in stability occurs right around the mass number 60. So once you consider nuclei with a mass number larger than 60, then it's going to have a higher probability of undergoing spontaneous nuclear fission. And so lastly here, we have nuclear fusion. And nuclear fusion differs from nuclear fission in that obviously we're combining two lighter nuclei, but it also does not require a neutron to occur. And so, like I said, nuclear fusion occurs when lighter nuclei fuse to form a heavier nucleus. And so this will result in a release of energy as kinetic energy for the reaction products, which are a helium-4 or an alpha particle and a neutron. And so the problem in fusion is that it's a little bit more difficult to achieve because as we know, a nucleus has both electric forces and nuclear forces. And so in order to get a nucleus to fuse together, it has to overcome the electric Coulomb forces that are often very strong in order to allow the nuclear forces to fuse these components together. So this is the entirety of the week 14 concept preview.